Okay, last little review video here. Again, I wasn't sure how much time we'd have. Figured just talk about the two main, the two biggest, not necessarily main, but the two biggest units that make up our test. And that is, our second one is dynamics. So dynamics, if you're like, what was dynamics again? This is forces, Newton's laws, friction. That's all dynamics. It's going to be a big part of the test. So I want to just review Newton's laws real quick because you will be asked some questions about these. You'll want to definitely memorize which is which if you haven't already done so. Newton's first law, so you can recall it in your brain real quick, and then we'll write it down. Newton's first law states that an object in motion or at rest tends to stay in motion or at rest, respectively, unless acted upon by an external net force, right? Again, this applies in space. We can witness this much easier in space because in space, when there's no gravity, there can be situations where an object is traveling forever and ever and ever and ever because there is no external net force acting on it. Gravity is an external force. So on Earth, this is very hard to witness, to visualize, because gravity is always acting on us. So there is that to kind of get in the way of things. But yes, we have to have an external net force, very important concept, right? If it's a balanced force, if I'm pushing on something like this from both sides and my forces cancel each other out, the net force is zero. And so it's going to still stay in motion or at rest because I'm actually not applying a net force. And that leads into Newton's second law. Do you remember Newton's second law? Think for a moment, see if you can. Newton's second law is a net force acting on a mass results in the acceleration of that mass. So if we do have a net force, it is going to be accelerating. That doesn't necessarily mean that, again, never mind. Sorry. I was going to say something and then never mind. We won't come to that. But I do want to say this. There we go. I forgot about that. So this is the formula that comes out of this law. F equals ma, but more importantly, F net equals ma. Because we can have a bunch of forces acting on an object, and that's going to be a lot of the problems on the AP test are going to be like that. All the forces acting on an object. Free body diagram, we're going to talk about that next. And the net force, the sum of all of those forces, result in the acceleration of that object. It's not just one force. We have to look at all the forces all together. And Newton's third law. Do you remember Newton's third law? What's missing here? For every action, there is an equal and opposite reaction, right? If I'm pressing on a wall, that wall has to press back at me. Otherwise, what would happen? My hand would go through the wall, right? The harder I press on the wall, the harder the wall has to press back. Now, of course, with some things, if I were really strong, or if the wall were made of sand or whatever, there is a maximum force that object or that surface could push back with. And if that force is exceeded, then yeah, the wall is going to crumble. So I know it's confusing to be like, well, how is it equal and opposite? That wall can't withstand a wrecking ball. So is it really pushing back with an equal and opposite reaction? Yes, it just means that the wrecking ball, the force that it came at the wall with, was more than the maximum the wall could withstand. The wall pushed back with its max, but it wasn't enough. It crumbled. Yeah, there is still an equal and opposite reaction if we have, again, two objects interacting with each other. So let's review the main types of forces here. So there's just these 5, but there's a few others. These are just the main types. Any others typically are derivative of these. So force of gravity is a big one, right? Force of gravity is the pull force an object feels due to gravity. We recall that this formula is mass times gravity, right? So I feel a different force of gravity than you do because our masses are probably different. Probably don't weigh the exact same thing. So this can get confusing, I know, but it's what an object feels we tend to get a little jumbled up with how this applies in the situation. It's the object itself feeling that force. So we want to make sure we understand that. Applied force is a contact force, right? So I've talked about I was pushing my phone, right? That's the applied force if there is a contact applied from one object to another. So that'd be an applied force. Sometimes we don't have applied forces. If an object is just sliding, there's no applied force. However, if an object is sliding, there could possibly be a force of friction, which always acts in the opposite direction of motion due to the contact between the object and the surface. Again, if you can recall, they've done experiments to figure out all these different coefficients of friction between different objects, because steel against steel versus paper against paper versus paper against steel, those are all different coefficients of friction. And that's actually, if you recall these formulas really quickly here, that U, remember that's mu. I just didn't want to look up the letter. It took me too long to find it. It's mu, right? That's the coefficient of friction for that particular situation. So static friction, we recall, prevents an object from sliding. So again, I could probably tilt my desk a little bit and not have things slide off because of static friction. But if I keep tilting, eventually they're going to slide, and then kinetic friction comes into play, right? Oops. Sorry. I was doing this quick, I guess. Didn't realize that. There we go. Force K. And sometimes, again, obviously, we'll see this as just force of friction if we just mean friction in general. But if we're talking about static versus kinetic, that's the S and the K. I should have done this next, but that's okay. And then again, times the normal force, which we'll talk about in just a bit here. We also have the tension force, which once again does not always apply in a situation, but this is force transmitted through a rope, a string, a cable, whatever. If I tied a string around my phone and pulled, that would be a tension force. It's not really applied, but it's more kind of like a pulling force. And the last thing, normal force, again, this is Fn. It is the force exerted by the surface perpendicular to the surface. So again, equal and opposite reactions. If I'm standing on the ground has to push up against me with an equal force of what I am being pulled down with. Gravity pulls me down, the normal force pushes up. But remember, if we're on an incline, the normal force is always going to point away perpendicular, right? Even though, again, gravity is pulling straight down, the normal force is exerted by the surface upwards. So the normal force would point perpendicular away from the surface. So looking here, just to remind us about a free body diagram, when you're drawing a free body diagram, make sure to label all applicable forces, even if you know certain ones don't matter. For example, if we're on a flat surface, oftentimes the normal force doesn't matter in our calculations, but it does exist. So you want to make sure that you label all of them. So I want to see if you can recall. This object is traveling down the hill, down a rough incline. Key here, rough incline. That means a certain force is going to be at play here because it's a rough incline. So I want to see if you guys can recall. Since we're on an incline here, we tilt our axis. This is the y-axis, this is the x-axis. See if you can draw on there all of the forces acting. I will tell you there are 3 forces acting on this object. See if you can draw them all. Well, we've got the force of gravity always points straight down. I'm going to label it. That's always where I go first. The normal force is pointing straight up. Now, yes, the normal force is going to be equal to the y component of gravity. If you can recall that, again, you'll want to be reviewing that stuff, because the normal force is the opposite reaction to the y component of gravity. But that is where the normal force goes. And then lastly, there is the force of friction. I could say either Fk or Ff for force of friction, pointing opposite. So that is a free body diagram. we'd have to break it down into components, do all that magic. We're going to practice some of those questions together as well.